Hello everyone, it's good to be with you again, and we're going to have some fun today because we're not going to go swinging through the trees, but we're going to be looking at tree diagrams. And of course, tree diagrams are part of probability. And so I need you to stay focused, remember all the rules that we've already established, understand the terminology, and let's make sure that we can be sure that at the end of today, we will get 100% for the probability of all the questions that we're going to get given in our tests or exams. And so I want to make sure that you've got all the concepts right. Let's have a look at our concept map. And so, yes, we're starting with tree diagrams, but we're going to get straight into talking about independent events. What are independent events? Remember, these are events that have an overlap. They are not mutually exclusive. And so we recognize not only do they have an intersection, but by definition, we have said that when we are to calculate the independent event, we recognize we must multiply the two probabilities together. So be very clear, it's the probability of X multiplied by the probability of Y. And what's this word replacement? Well, guys, replacement is a process that we do when we're having a probability trial. So for example, if we were taking socks out of a bag, then we would need to make sure that once we've removed one sock, before we do the second event, we would have to put it back. And that means that the total number in the sample remains the same. So the probability of the first event does not influence the probability of the second event. Let's be specific and let's use an example to illustrate this. So we're told that in this drawer, we are going to select some socks, and in the drawer, there are 5 black socks, there are 3 white socks, and 2 red socks. Now, you recognize that the total number of socks in the drawer is 10. And if we were to calculate the probability of putting our hand in and selecting randomly, we wanted to know what the probability of the red sock is, then, or the white sock at least, sorry, white sock, the probability of the white sock, we know that there are 10 in the total sample. The number in the sample is 10. The number of white socks is 3, so it's going to be 3 out of 10, which is a probability of 0.3. Now, that would be fine, and we recognize that's one event. We'd be able to calculate the probability for the other socks as well, using the same probability formula. But let's say that we have a second event. This time we're going to take that white sock and we replace it. We put it back into the drawer. Do you see that the number in the sample is now still 10? So when we do the second pulling out of the sock, we're going to be able to calculate the probability in exactly the same way. So if we do the second situation, we'd recognize that the probability of selecting a white sock is still going to be 3 out of 10. And that's because we had replacement. The probability of the first event did not influence the probability of the second event. And that's what makes these two events independent. Remember that when we're doing these sort of calculations for independent events, that when we have the two things multiplied together, and we say the probability of A multiplied by B, that intersection is going to be the probability of A multiplied by the probability of B. So be very clear about that rule for independent events. But what about dependent events? Dependent events take place when there is no replacement. So in the same scenario, for my first situation, take a look. The probability of the white sock for the first trial was, you agree, 3 out of 10. Now, if I am going to take out another sock, and I'm not replacing the sock that I took out. There are two possibilities. The one possibility is in the first event, I could have taken out a white sock. Let's say I took out the white sock. Then in the second event, then notice what I've got. This is the probability of the second event. There's no replacement now. In the second event, how many white socks are left? Well, if I didn't put the white sock that I took out back, then I've got one less white sock. So I've now got 2 white socks. What's the total sample space? Well, the total sample space is no longer 10, it's 9. So if you look here, it would be a probability of 2 out of 9. And can you see, by taking the first probability, the second probability has changed. If I didn't choose the white sock in the second time, there is an alternative. If I didn't choose a white sock, then I could still have had 3 white socks left in the drawer, and I've still got 9. But the probabilities are not the same as they were at the beginning. So that's the definition for a dependent event. Remember here again that we cannot find, if we've got the intersection of those 2 events, we cannot use the multiplication formula. In fact, if we multiply the 2 things together and we find they're not equal, then they're not independent. And we've recorded that in this statement over here. Remember, for dependent events, they are not mutually exclusive, so there will be something in the intersection. We also recognize the probability of the one influences the probability of the other, but this identity doesn't hold true. They're not equal because they are dependent events, not independent events. So let's focus now as we look at these ideas of independent and dependent events together with all the other rules that we have on what a tree diagram is. A tree diagram is a graphic representation of what happens when we have a series of events that can be following on, a series of choices that can take place on a particular day. And the tree diagram is very useful for representing all the outcomes. And then by looking at that, we can also see the probabilities of various things taking place, and we can do some calculations. So it illustrates all the possible outcomes of multiple events. Let's have a look at an example. So if you are given the famous choice at a restaurant of chicken or beef, and then on top of that, chips or mash, we can represent all the possibilities in this tree diagram. We start off at a point and we draw a line. That C represents the chicken, this represents the beef, and we are recognizing that is one choice. At this point, we can then choose to either have chicken and chips or chicken and mash. And so we've got another set of choices, and we've represented that by a fork in the tree. So in this situation, this outcome is chicken and chips. This outcome is chicken and mash. This outcome would be beef and chips. And this outcome would be beef and mash. And so we can see all the possible outcomes, possible combinations of making those choices. Now, what's also very interesting is that when we get problems to solve with tree diagrams, we're often given different probabilities, because there's no chance, really, that most people will choose chicken or beef. It won't be a 50-50 chance. It will be some probability. But what's important to look at is these 2 choices are mutually exclusive. And so when we look at them and we put the probability over here, let's say that this is 4 out of 5 people are going to choose chicken, that means that 1 out of 5 chooses beef. Those 2 numbers add up to 1. And the same thing happens over here, where we have chips and mash. let's say that there are 3 out of 5 choose chips and 2 out of 5 choose mash. Again, these numbers add up to 1. So in the same way, we can get proportions over here. We could say when we're having beef, there could be 3 out of 5 as well, and 2 out of 5, but those numbers will add up to 1. And so there becomes the addition rule, the adding together of mutually exclusive events. Remember, you can't be chicken and, or chips, and they don't happen at the same time. It's together. You're wanting chicken or chips, that combination together. You can't have a choice of chicken or beef. You can't be chicken and beef on the same plate. That's not allowed. In the restaurant, you either have chicken or you have beef. So that's in the sample that you've got. It adds up to 1. Concludes all the elements there, so they're mutually exclusive. You can't decide that you're going to have chips and mash. That's not allowed. But what I want you to see is along the stem, you can get combinations now that are multiplications. These ones were all. That was all. That was all. But along this way, we're going to get and. Okay? And so we can determine the probabilities by multiplying these things together and getting the outcomes out of the total. I hope that gives you a grounding of what a tree diagram is. You might have encountered them sometime before. They're a lot of fun, but you have to be careful to put all the information into the tree diagram. So let's take a quick break. After the break, we'll be back to discuss some particular problems.